This week we're talking about group theory. So let's recall a group, G, is a set of elements with a binary operation. It's always written either as multiplication or addition with these properties. The first is associativity. And in general, I'm going to write things for a multiplicative group, and the translation for an additive group is always straightforward. So for all elements x, y, z in the group, if you multiply x, y, and then multiply that by z, that's the same as x times the product of y and z. Second, there exists an identity element. So there is an element E in the group such that if you multiply E by x on the left or the right, you always get x for every x in the group. Third property is existence of multiplicative inverses. For all x in the group, there exists a y in the group such that if you multiply x on the right by y, or if you multiply x on the left by y, you get the identity. That's it. Those three properties define a group. So any group with any set with a multiplication that is associative, there exists a multiplicative identity and multiplicative inverses, that's a group. Now, some groups have an additional property, which is called commutativity. So the commutative property says that xy equals yx for all x and y in the group, and a group G is commutative or abelian if multiplication in the group is commutative. And we will see a very wide collection of objects that are groups. Things that you're familiar with and things that you are not so familiar with. In mathematics in general, and in algebra in particular, we prove things. And we will prove many lemmas and theorems about groups. So the first lemma says that in a group G, the identity element is unique, and every element has a unique inverse. Proof. Suppose we have two elements, so that E and E prime be elements of the group such that EX equals X for all X in the group, and XE prime equals X for all X in the group. So if E and E prime were identities, they would have these properties. And then we do the following very simple calculation. Where we have X E prime equals X, let X equal E. And then this equation says, this is true for all X, so it's true in particular for E. So E prime equals E. Actually, I can make it easier. From this, we have that E prime equals E prime. And from this, letting X equal E prime equals E. So E prime equals E. So that shows the uniqueness of the identity. Now, a lot of times in mathematics, things are so simple, they're hard, or they take a while to understand. So you have to spend some time to understand why this equation and this equation imply the uniqueness of an identity. But they do. Now let's prove that the inverse of an element is unique. So let X be an element in the group G. Suppose we have two elements, Y and Z in G, such that XY equals the identity and ZX equals the identity. So now we perform the following very beautiful sequence of steps. I want to show Y equals Z, that there's only one identity. So Y, of course, if you multiply Y by the identity, it's Y. But we can write Y, we can write E as Z times X. And by associativity, this is Z times XY. But XY is equal to E. And Z times E is C. So Y equals Z. And that is the end of the proof. A simple example, but the most important example of an additive abelian group is the set Z of integers. Under addition. And you can check it has all the right properties. Suppose I let 2Z be the set of even integers. 0, plus or minus 2, plus or minus 4, and so forth, the even integers. So 2Z is also a group, and it's a subset of Z. 2Z is a subset of Z. So this is an example of a group and a subgroup. A subgroup of a group is a subset that is itself a group. So let's give the formal definition of a subgroup. So a subgroup of a group G let's say the identity element in the group is E. A subgroup of a group G with identity E is a non-empty subset H of G such that the following three properties hold. First of all, it contains the identity. Second, it's closed under multiplication. So if X, Y are in H, then the product X times Y is in H. And the third property is it contains the inverse of each of its elements. If X is in H, we know X has an inverse in G. H is a subgroup. If for every X in H, then X inverse is in H. And I should have observed that we denote the unique inverse of X by X to the minus 1. So this is the inverse of X. And there's another lemma. All these things are in the set of notes called Notes on Group Theory, which I've just posted on Blackboard and emailed out to you. So first of all, a subgroup of a group is a group. Well, it contains an identity. It's closed under multiplication. It has an inverse. The only thing you need to check is that the multiplication is associative. And multiplication in G is associative, and that property carries over to the subgroup. A subgroup of an abelian group is always abelian. And we have a kind of chain condition. If H is a subgroup of G and K is a subgroup of H, then K is also a subgroup of G. So we have a group G. It contains H as a subgroup. H contains K as a subgroup, but K is also a subgroup of G. Now, it can happen that groups look different. They have different elements, maybe the same number of elements, but different elements, and different binary operations, but somehow they're really the same. They just superficially look different. So here's an example. Suppose we take a set consisting of just two numbers or two symbols, 0 and 1, under addition. And the addition rule is 0 plus 0 and 1 plus 1 equals 0. And 0 plus 1 and 1 plus 0 equals 1. So this is an additive. If you check, you can, I mean, you have to check a lot of things, but this is an additive abelian group. Suppose H is a set consisting of the letters E and A with a multiplication. E squared equals A squared. E squared means E times E. A squared means A times A equals E. And EA equals AE equals A. So these are different sets, and this has addition as its binary operation, and this is multiplication. But I can define a function from G to H by setting f of 0 equals E and f of 1 equals A. So that defines a function. And this somehow, and this is 1 to 1 and onto, the 2 elements here and 2 elements here. If we take f of 0 times f of 0, that's E times E, which is E, which is f of 0, which is f of 0 plus 0. And if we take f of 0 times f of 1, that's E times A, which is A. A is equal to f of 1, which is f of 0 plus 1. And we can check similarly that f of 1 times f of 0 is f of 1 plus 0, and f of 1 times f of 1 is f of 1 plus 1. So somehow this function f is identifying the binary relations between these two sets. And from the point of view of algebra, these sets are the same. The word for the same in much of mathematics is isomorphic. And let me give you a sort of a formal definition of what isomorphism is and what an isomorphism is. So let G and H be groups. A function f from G to H is called an isomorphism if f of x1 times x2 is equal to f of x1 times f of x2 for all x1, x2 in the group. And the function f is 1 to 1 and onto. So when you have two groups, G and H, and a function from G to H that's 1 to 1 and onto, it establishes what we call 1-to-1 correspondence between the elements of G and the elements of H. Every element of G gets mapped to some element of H. In H, every element is the image of something in G, and two different elements in G always get mapped to two different elements of H. That's a 1-to-1 correspondence. And if we satisfy this sort of functional equation, then this 1-to-1 correspondence is called an isomorphism, and we say that the groups G and H are isomorphic. Now, there are some simple lemmas in the notes with proofs. So if f from G to H is an isomorphism, this function has an inverse. Then there is a function f inverse from H back to G such that, so let me sort of draw a picture. We have G and H. We have a function f from G into H. We have a function f inverse from H back into G. If you compose F inverse with F, that goes from G to H to G. That's the identity function on G. And if you compose F with F inverse, so you start at H, you go to G and back to H, that's the identity function on H. So if you have an isomorphism, then there's an invert from G to H. There's always an inverse function from H back to G. And F inverse itself is an isomorphism. One more important result. We'll call this one the theorem. Isomorphism of groups is an equivalence relation. So what does this mean? First of all, G is isomorphic to itself for every group G. So this says that isomorphism is reflexive. Second, if G is isomorphic to H, then H is isomorphic to G. So this relation of isomorphism is symmetric. And if G is isomorphic to a group H, and H is isomorphic to a group K, then G is isomorphic to K. So isomorphism is transitive. So that means we have an equivalence relation. And the proofs of these are not very hard. And again, I wrote them in the notes. And I can talk about them in the Zoom session if anyone has a question. Okay. So in this section called Notes on Group Theory, this is the end of section 1.